This video will cover the fundamentals of data representation, sound. To begin, I'd like to reference the wikibooks.org site where I've borrowed some of the material. Sound waves are analog. It's a continuous signal. A large size equals larger volume, and an increase in frequency equals a higher pitch of sound. We have examples of this here. We double the volume, the frequency here, volume, and here we have a higher pitch with increased frequency. Computers sample sound at discrete points to create digital representation of sound. So we have the continuous analog signal here, and then we have the computer sample with time going across this way. So we take samples at intervals and we create representation. We lose a lot of the data in between these samples, and if we increase the sample rate we take more measurement points, and therefore we get a better representation. So here's a diagram that represents the sound waves recorded through a microphone. The microphone produces an electrical voltage which goes into an analog to digital converter. This goes inside the computer, which can't handle the analog signals, it can only understand digital ones and zeros. And when we're sending the sound out of the computer, we use a digital to analog converter to convert it back into an electrical voltage, so that we have a speaker, which is a piece of cardboard and a magnet which vibrates, and that creates the sound waves or the analog signals which we can hear. Let's consider some ways that this is encoded. We have a sample rate, sampling rate, which equals the number of samples taken per second. We also have the sample resolution, the number of bits assigned to each sample. A CD, for instance, is generally a 16-bit sample to get some high quality. So we have the number of samples taken per second, and we have the sample bit. We have a bit rate, the number of bits required to store 1 second sample of sound. And a bit rate is calculated by multiplying the sample rate by the sample resolution. A file size equals the sample rate times the sample resolution times the length of the sound. Or we could say the file size equals the bit rate times the length of the sound. Let's look at this example. If we want a 30-second voice message on the mobile phone, we have a sample rate of 8000 Hz or 8 kilohertz, a sample resolution of 16 bits, and the length of the sound will be 30 seconds, a 30-second voice message. And we can calculate it by multiplying 8000 times 16 times 30, which equals 3 million bits, divided by 8 will give you the bytes, because there's 8 bits in a byte. 8 bits in a byte. Let's do this calculation. So we have 8000 times 16. And this gives us the bit rate. The sample rate times sample resolution gives us the bit rate. This is the sample rate and the sample resolution. So now we have the bit rate. So if we multiply the bit rate times the length of the sound, which in this case is 30 seconds, so times 30, gives us the file size in bits. If we want to look at it in bytes, we divide by 8, divided by 8, and now we get 480,000 bytes. Let's go back to the sample rates, the number of samples taken per second. This screen capture here is the same sound in Audacity, which is freely available. You can download it, and we have it on the computers at school. So we have one at 8 kilohertz or 8000 hertz. We have one at 22 kilohertz, and we have one at 44 kilohertz. So you can see that the higher the sample rate, the more data points we have per second. So it more evenly follows the continuous signal. So you get a high quality sound. However, you'll also have a larger file size. Now we'll consider a 3-minute pop song recorded at sample rate of 44 kilohertz and a sample resolution of 16 bits, which is typical. 44,000 times 16 times 180 equals roughly 15 megabytes. An MP3 of the same song, however, would be about 3 megabytes. So that's a great reduction. And we achieve this using a form of compression. The compression will make the file size smaller, and there are two main types of compression we're going to consider. We will consider lossless compression, compression that doesn't lose any accuracy and can be decompressed into an identical copy of the original audio data. So such, for instance, a WAV file is uncompressed, and a lossless compression method will have about half the size and use run length compression. Here's an example of run length compression. If our data consists of a large number of zeros followed by some other numbers, then another larger run of zeros, we use the run length of this data to say that we have 21 zeros followed by these numbers, followed by another 17 zeros, followed by this number. So you can see the data is shorter, but with this I can recreate this exactly by just adding 21 zeros here and 17 zeros here. Lossy compression with MP3s loses file accuracy, and generally the file size is smaller than lossless compression. And MP3 uses perceptual encoding. So perceptual, what we perceive, is psychoacoustic models. So this is using psychology, acoustic models that discards data that is less audible to the human hearing. So basically, in short, you lose some very low frequencies and very high frequencies. The quality of the sound isn't as good, but most people won't notice the very high frequencies and very low frequencies that are lost. You should be familiar with Nyquist's theorem, which helps us to understand what sample rate we should use. And Nyquist theorized that the sample rate should be at a frequency which is at least twice the value of the highest frequency in the sample signal. Therefore, the minimum sampling rate that satisfies the sampling for a human ear is 40 kilohertz, 2 times 20 kilohertz. 20 kilohertz is our range of hearing. So if we multiply that by 2, we get 40 kilohertz. And the 44.1 kilohertz sampling rate is used for the compact discs, and it was chosen for this reason and other technical reasons. So the human ear is 20 kilohertz. We sample at twice that, and we get 40 kilohertz, or round about that, 44 kilohertz here. You should also be familiar with the fact that it is possible to synthesize sound, to create sound. So sound synthesis, rather than sampled sound, is electronically generated sounds that mimic musical instruments or the human voice, or indeed a unique and original sound. So synthesis creates sound, whereas everything we've been discussing so far is a sample of sound, a recording of sound, but this one generates the sound in the computer. And finally, in considering audio, we should be aware that downloading audio, generally you have to download the whole file to play it. If I download an MP3, once the entire file is downloaded, I can play it. With streaming audio, indeed also with streaming video, you can begin playing the audio while this is downloading. So the data stream is coming into your computer, and as soon as some of it has buffered in your memory, you can begin playing it while the rest of it is being downloaded. And there are a couple of different methods. Unicast connections require multiple connections from the same streaming server when it starts. So here's the streaming server. We have multiple connections. Multicasting broadcasts the same copy of audio to the entire network. And you can read about the advantages and disadvantages of these and be familiar with them. And that concludes audio. Thank you.